So today we're going to be talking about rule-based systems, which we saw in lecture. But we'll be talking about it in a little more technical detail with these rules that have a strict format. So we're going to start with a few definitions. So a rule has an if part and a then part. The if part is called the antecedent because it comes before. Then the then part is called the consequent because it's like a consequence of the rule. And together those make a rule. Some rules also have things like or and, which are fairly self-explanatory. And then these weird question mark things are variables. That's a notation that comes from lists. So we have rules, and here we have a list of 6 rules. And then we have these things labeled A0 through A3, which we'll call assertions. So assertions are statements that in the system we assume to be true. So we assume that Neo is a noob, and in the system that's always true unless we have a delete rule that causes the assertion to go away. So you could think about these rules and these assertions and draw some conclusions by applying the rules. And there are 2 main ways of doing that, called forward chaining and backward chaining. So in forward chaining, and we're going to look at both these today. In forward chaining, we're going to start with these assertions and keep applying rules until there are no more ways that we can apply the rules, and we'll get a list of all the possible assertions you can get from the system. In backward chaining, you can start with a specific hypothesis. For example, we might want to find out whether Neo is the one. So this is a statement that we don't know whether or not it's true. But if you were to look at these rules for a while, you could probably figure it out. So in backward chaining, you start with this hypothesis and build a goal tree to figure out what would need to be true in order for that to be true. So we'll start by doing forward chaining, and then we'll try backward chaining on that hypothesis. So forward chaining goes in iterations, and in each iteration there are 2 main steps. First, we're going to go through all of the rules and see which of them have an antecedent, the if part, that matches one of our assertions. We'll go through all the rules. And for each rule, check whether it's antecedent. Matches the assertions. And if so, we'll say that that rule matches. So each such rule matches. So we're going to make a table to keep track of which rules match in each iteration. So we'll keep track of the iteration number and then which rules match. So in our first iteration, we're going to look through all of these rules and see which ones of them have an antecedent, the if part, that matches some of these assertions. So if you find a rule that matches, just shout it out. Rule 0, P0. Yeah, so that's or. It looks like that could match with either A0 Neo is a noob or A1 Trinity is disenchanted. So we'll have to figure out how to deal with that. Are there other rules that match?
P4.
P4. So we need both X is disenchanted and X loves Y. It looks like that works with X is Trinity and Y is Neo. So P4 matches. Do any other rules match? No? I'm seeing some no's. Okay. So we're done with that step. So then the second step is we're going to iterate over all of these rules that match and see which ones could produce new assertions. So for each matched rule, we'll check whether it could produce new assertion. We'll say that the first rule, for which this is true, fires. So if we go through these rules, we'll look at P0 first. Could P0 produce a new assertion? Yeah. P1. Did someone say P1? What can P1 do?
Well, it visits the, like, Neo visits the oracle, so it matches that rule. I have to see it for P2. Sorry, yeah, for P1.
So it looks like, I don't think we have visiting the oracle quite yet.
Okay.
So if you had Neo visits the oracle in your list of assertions, then that rule could fire.
Okay.
But in this case, that rule doesn't match, so this is going to have to be one of the rules that already matches. P0? Yeah.
Well, so is the variable x and y like the same for all set of rules, or is it local to just one rule?
Good question. They can be different across all the rules.
And,
So really, a more clear way of stating this would be to use different variables for each rule.
and then also for P0, does it short circuit because x we're using Neo as x in the first one, and then Trinity is y in the second one?
For P0,
It's an or, it's an
It's not or. It's or, but then like so that then is that x Neo or Trinity?
yeah, so P0 will actually fire 2 separate times. That's how we're going to handle that. Yeah, so what we're actually doing here, I just said for each matched rule, but really what we're doing is it's sort of a nested for loop where if we write it in pseudocode, first we're iterating over each rule. And then within that, we're iterating over each assertion. And then we'll do some stuff. So in this case, P0 matches in 2 different ways. So we're going to look at the assertions in order, and it looks like A0 is the first assertion that could cause P0 to fire, so we're going to handle that one first. So in this case, P0 will fire with X being Neo. And that will produce some new assertion. So the first such rule fires. We'll add the new assertion to the list. So what new assertion do we get from firing P0 with X as Neo? Yeah.
You get that Neo visits the oracle?
Mm-hmm. We're going to call that assertion A4. So we could just add it to this list, but in this case I'll write it in the table. But this is a new assertion that we're adding to our set. We have Neo visits the oracle. We're only going to fire one rule each round. So we're going to say the first such rule fires, and then the round is over. And the iteration is over.
So on the quiz, we also expect the number and do everything in top-down order, like we did P0 before P4, and then we number A4. So
Yeah, so on a quiz you would be given this set of rules and assertions. Actually, this problem is from a quiz, if you want to look it up later. It's from 2010, quiz 1. So yeah, you would be given the rules and assertions and probably asked to fill in a table like this, where you figure out in each iteration which rules match and fire. So the reason why we're only going to fire one rule in each round is because if we had a more complicated system, for example, with not or delete rules, then it's possible that you would have some contradiction. Like if you had one rule that produces the assertion Neo visits the oracle, and another one that says if this, then delete Neo visits the oracle, it would be hard to fire those both at once because they would be in conflict. So for that reason, we fire only one rule per round. In this case, where it's a fairly simple system, it doesn't make a difference. But this way, the same procedure can apply to a more complicated system. So then we're going to, yeah.
So then in iteration 2, would you match before again, or would you do something else?
Yes, we'll get there in a moment. So the end of this is we're going to continue this procedure until no new rules fire. So yeah, in the second iteration, we're going to see which rules match again. Will P0 and P4 ever stop matching as we go through the iterations?
How would that delete?
If you had a delete, then they could, or a not. But in this case, because we don't have any not or delete rules, they'll always continue matching. So that means we still have P0 and P4 matching. Are there other rules that match now?
P1.
P1. So now we have this new assertion, and that causes P1 to match. Anything else? P2? Yeah, because we have Neo visits the oracle, so P2 also matches. It looks like P3 and P5 don't match yet because they both require the oracle says someone is not the one. And we don't have that in our list of assertions yet. So which rule fires now? Can we fire P0 a second time? Seeing yeses and nos. So we just want to find the next rule that can produce a new assertion. Can P0 produce a new assertion? Someone who's saying yes, why? Yeah.
Does it say that journey visits the oracle?
Yeah, we can fire it again with x being trinity. So we can fire P0, this time with x is trinity, and we'll end up with the new assertion A5 trinity visits the oracle. So a rule can fire multiple times.
Why don't we let it fire multiple times at the same step?
Yeah, so that's again because of this technicality of we want it to be an atomic procedure in case there are complications. It's unlikely that you would run into a problem when it's the same rule, but mostly because that way there's a specific procedure that we can follow, so it's well defined. So that way you only have one binding of variables to words at the same time. So what happens in round 3? Do any new rules match? No, because P3 and P5 still require the oracle to say something, and we don't have any of that. So it's just going to be those same rules because they're not going to stop matching. Can we fire P0 a third time?
No.
No, because there aren't any new bindings, so we can't get any new assertions out of it. How about P1? Who's going to be X? Yeah.
Because it was the first assertion to be like, it was created before A5.
Yeah, exactly. So this is again the thing where we're following the assertions in order. So Neo visits the oracle comes before Trinity visits the oracle. So we'll do X as Neo first. So what's going to be assertion A6? Neo picks the one.
Okay, so we can't use assertions by default if we go like 2 levels up, is that?
No, so it's actually, so you could use Trinity visits the oracle, but what's actually going on here is we're iterating over the assertions in order. So because Neo visits the oracle is earlier in the list of assertions than Trinity, we're going to fire the rule with that one first. So it's just a tie-breaking rule. Okay, so what about iteration 4? Now do we have any new rules matching? No. Because we still have the problem where P3 and P5 require the oracle to say something. Can we fire P0 or P1 again?
P1.
P1, yeah, Trinity. We get A7, Trinity fix the 1. So we're learning lots of new things about the system, but we haven't figured out anything about whether Neo is the one, if that's our goal. So you can see that forward chaining might be kind of inefficient if we're trying to figure out a specific thing, but it will tell us everything that we can possibly learn. So here we just have the same rules matching, and we still don't have the oracle saying anything. Can we fire P0 or P1 again? No, how about P2? Does P2 work? Who's X? Neo. What assertion do we get?
Can you get two assertions at once?
Yes, exactly. Yeah, so here we have add new assertion to list of assertions. In some cases, there might be multiple new assertions. And that's in this case where the consequent, the then part, has two statements. So if those are both new assertions, then we'll add them both to the list. If one of them was already in our list of assertions, then we won't add it. So A8 is going to be, the oracle says, Neo is not the one. What's A9?
Neo is disenchanted.
Neo is disenchanted. Okay, so now do P3 or P5 match? We finally have the oracle saying something. P3. Yeah, so P3 has this complicated OR node inside an AND node. And now that matches. We have P0, 1, 2, 3, and 4. Does P5 match? Not yet. Let's see. So we need the oracle says X is not the one. That could be X is Neo. We need Y proclaims love for X, which could be Trinity and Neo. And then we need Y picks the one. Do we have Trinity picks the one? Yeah, we have that here. So it looks like P5 does match. So now all of our rules match. So which one is going to fire? Yeah.
Okay, just like a quick question, going way back. P0 says like, oh, like question mark X is a noob, like, and then like X is disenchanted. It doesn't matter that it's like using Neo for like the first one and then changing.
Yeah, so that's because this is an OR node. So if that was an AND, then you would need them to be the
I
same.
see.
But in this case, you only need one of those things to be true.
Okay.
So yeah, that's a good question. When we fired P0 twice, it was using different parts of that OR node,
Okay.
for the OR clause. So which rule is going to fire here? Which one can give us a new assertion? 3? Who is X? Yeah. So that'll give us A10, which is hold on, this is P3?
No.
Looks like we already have the oracle says Neo is not the one.
Oh.
Oh, sorry, I'm reading this rule
practices
wrong.
come through.
Yeah, there we go. Neo practices come through. Okay, so then what happens? All these rules are going to just continue matching forever because we don't have any nuts or deletes. Do we fire P3 again? No, what about P4? assertion would P4 produce? What about P3? Oh, A3. Yeah, exactly. So if we tried to fire P4, it would produce Trinity proclaims love for Neo. So that's already in our list, so we're not going to fire it. How about P5? Yeah, P5 can produce a new assertion. So we can have X is Neo, and Y is Trinity. And we'll get A11, Neo is the 1. So if we were just trying to figure out, yeah, go ahead.
So for P4, like in an actual implementation of this in code, like when you have to like execute it just to see if you already have the assertion?
Yes, so you would have to check what assertion P4 could produce, and then see whether that was in your list of assertions. So now if we were just trying to find out whether this hypothesis was true, we would be done because we've concluded that Neo is the 1. But the forward chaining procedure technically continues forever until we produce all the possible assertions. So we're going to keep going and see if we can get any more assertions. So in round 8, everything matches. Which rule would fire? It might be a trick question. None of them. So there aren't any new assertions we can get from any of these rules. In some cases, it's possible that one of the older rules, like maybe P0, might now match in a new way, and so we could go back and fire P0 again. But in this case, there's nothing else we can do. So it looks like we've concluded all of the possible assertions that we can get from the system. Yeah.
So like if you were just looking for that one assertion or whatever, would you still have to keep going in case it like got flipped? Or
Oh, that's a good question. Yeah, in case it got deleted.
Or can you just like leave it?
So that's why systems with delete are very complicated. You're unlikely to see that on a quiz because that is a problem that it's possible if you had a delete rule that later on they would say delete Neo is the 1. So I guess then you would want to continue going until you produce all of the assertions to see if that ends up getting deleted. That's a good question. But you won't really have to deal with that in this class.
Okay.
Was there another question? Okay, so that's forward chaining. Oh, yeah.
Do they always end? Or could it ever like just not end?
Yeah, it's possible that you could get stuck in an infinite loop. So if you had, here's a kind of silly example. Let's say that in some other system you have a rule P0 if X is happy. Then X smiles. Oh, actually, this won't. No, I don't think you'll get stuck in a loop. This will get stuck in a loop in backward chaining. Well, we could have a very nonsensical rule. If X smiles, then delete X smiles. And if we started out with only one assertion, say, Annie is happy, then you would end up first producing Annie smiles, and then deleting Annie smiles, and then producing it again, and then deleting it again. So that would just go on forever. So it's possible that in some cases it might never terminate. But if you don't have not or delete rules, I think it always will. Any other questions on this? Okay, let's go on to backward chaining. So now let's say that if all we care about is Neo is the 1, we really don't need to know all of this information. So we could just start with Neo is the 1 and see what needs to be true in order for that to be true. So backward chaining is going to be a recursive process because we're building a goal tree. Check whether our hypothesis is in our list of assertions, because if it is, then we're done and that's easy. have our hypothesis, Neo is the one. We're going to reset our list of assertions to be just these four. The forward chaining added a bunch of assertions, but in backward chaining, you'll only have those starting assertions, and you'll never add new ones. So is Neo is the one in the list of assertions?
No.
No, so we're not done. We have to keep going. Okay, so our next step is we're going to find, yeah.
What if like the not of the assertion isn't like what the not of your hypothesis and the assertions? Like would you still go through to see if that gets flipped? Or
What do you,
but let's say like A4 was
Neo is not the one?
Like would you still do that?
Yeah, so that brings up a good point. So this system actually doesn't know what anything means. It doesn't speak English. So that means if you had an assertion like A4, Neo is definitely the one, it wouldn't match. So if you had Neo is not the one in the assertions, then that also wouldn't match. So it's only doing this very brittle string matching where you have to have the exact string. So now we're going to go through and find all of the rules that could produce Neo as the one. So more specifically, we're going to find all of the rules that have a consequent, the then part, that matches the hypothesis. So which rules have a consequent that matches Neo as the one? P5. It looks like P5 is the only one. So now we're going to build a goal tree using these rules. In this case, there's just P5. So we'll construct a goal tree. This is like what we saw in lecture. We're going to say it's a goal tree of bound antecedents.
Was this also a question on the quiz that you talked about earlier?
Yes.
Okay.
Yeah, so both of these questions that we're doing are on 2010 Quiz 1, which you can look up from the website. So bound antecedents just means that we're going to take all of the things in the antecedent of P5, the if part, and we're going to bind the variable Neo to X. So we're going to draw some sort of node here. Is this going to be an AND node or an OR node? AND node, because we have an AND in this rule. So this is AND node. It has the crossbar that looks like an A. And then we're going to write down the three things that need to be true in order for us to conclude that Neo is the one. So we have the oracle says Neo is not the one. What will be the second one? Yeah.
Is that just somebody proclaims love for Neo as so long as the somebody is the same as the other antecode?
Yes, exactly. Yeah, so we don't care who proclaims love for Neo. As humans, we can look at this set of assertions and we go, obviously it's going to be Trinity because Trinity is the only person proclaiming love for Neo in our assertions. But the system doesn't know that. So we're going to just leave like an unbound variable there and say Y proclaims love for Neo. Yeah.
Are X and Y, for instance, permitted to be the same person?
Yes.
Okay. So
Yeah,
it
so
could
if
be
you had-
Neo proclaims love for Neo.
Yeah, so if you had an assertion Neo proclaims love for Neo, that would match. The system doesn't care whether those are the same variable. And then the third one is also going to be Y. And so we don't care what variable this is. You could call a variable P instead if you want, but they need to be the same variable in order for this rule to produce Neo as the one. So here we have Y fix the one. Okay, so now we have the beginnings of this goal tree. Now we just need the recursion step, which is we're going to do depth first assertion. Another thing we're going to do is we're going to keep track of which hypotheses we tried to look up in our list of antecedents. This is something when you look at the quiz, you'll see that we ask you to do this on the quiz just to keep track of what order things are happening in. So if we were to write a list of checked hypotheses, the first one would be Neo is the one, because that's the first thing we tried to look up. So I'll put a 1 next to that. What would be the next thing if we're doing a depth first search? The oracle says Neo is not the one. So we could write that in this list, but for now I'm just going to number it in the tree. So now we'll follow the same procedure using the oracle says Neo is not the one. That's our new hypothesis. So is that in our list of assertions? No. So we have to go on to step 2. Which rules could produce this statement? P2. What would we do if there were multiple rules that could produce the statement? What's that? Go in order? Yeah, you could do that. Another thing you could do is put them both on the tree and connect them with an OR node. So if, say, P2 and some other rule, P6, could both produce this, then you could put them in an OR node because you only need one of them to be true in order to get the statement. But for now, we just have P2. So what kind of node is P2? An AND node. So there we have Neo as a noob, and Neo visits the oracle. So which hypothesis do we check next? Neo is a noob. Is that in our list of assertions? Yeah, so we're done with that branch. Do we need to know whether Neo visits the oracle? Yeah, because that's an AND node. So we'll go there next. Is that in our list of assertions? No. So which rules could produce that? P0. Are there any others? No, just P0. Looks like P0 has an OR node because it's an OR. So we need either Neo is a noob or Neo is disenchanted. So you might ask, why do we need to check Neo as a noob again if we already know that it worked? And the answer is this system is kind of naive. In the same way that it's only doing brittle string matching, it also doesn't keep track of what it's seen before. So sometimes it will be inefficient and go through the same subtree again. In this case, luckily, the subtree is fairly short. So we can just look up Neo as a noob, and it's still on our list of assertions, so we're good. The list of assertions never changes. Do we need to know whether Neo is disenchanted? No, we don't, because that's an OR node. So here we can do something called short circuiting, where we don't need to look at anything in this subtree, because we already know that Neo is a noob means that Neo visits the oracle is true. So this is called short circuiting. Similarly, you could short circuit an AND node if you discovered that the first branch is false. Then there's no point in checking the remaining branches because the entire node will be false. So which hypothesis do we look at next? Y proclaims love for Neo. So this is a slightly tricky thing. In our list of checked hypotheses, we're looking up Y proclaims love for Neo, and it's not a specific person. So is that in our list of assertions? Yeah. So it looks like that matches Trinity proclaims love for Neo. So we can say, yeah, that's in our list of assertions, and just to keep track of what's going on, Y is Trinity. So what will be the seventh hypothesis that we look up? Are we looking for Y picks the one?
Yeah.
Trinity picks the 1. Because now that we know that this y is Trinity, we need this one to also be Trinity. So the 7th thing in our list will be Trinity picks the 1. We can mark that here, y is Trinity. Okay, so is that in our list of assertions? Yeah.
What if the y in there is not actually Trinity, but we have the assertion that Trinity loves Neo?
Yeah, good question. So what if y could be someone else? We're actually going to look at that as a hypothetical situation at the end of this problem. So for example, what if you had another assertion that someone else proclaims love for Neo? That's a more complicated situation that you're unlikely to see on a quiz, but you would have to backtrack and go back and try a different way of binding the variable. So is this in our list of assertions? No. Which rules could produce Trinity picks the 1?
P1.
P1. What kind of node is P1? It's a trick question. It's just a straight line. So P1, we would need someone visits the oracle. We would need Trinity visits the oracle. Okay, so this is the next hypothesis we're looking at. Is that in our list of assertions? No. What can produce Trinity visits the oracle? P0. So P0, or node. So we need Trinity is a noob or Trinity is disenchanted. What do we look at next? Trinity is a noob. Is that in our list of assertions? No. Do we have a rule that could produce it? No. So now what? It looks like there's no way of getting Trinity as a noob. Are we just done? Do we give up?
No.
Yeah, it's an or node. Excellent. So we can keep going. So how about Trinity is disenchanted? Is that in our list of assertions?
Yeah.
Yeah. Okay. So we're good there, and that means that Trinity visits the oracle is true, which means Trinity picks the 1. So Neo is the 1. So now we've managed to do that. Oh, this was number 10. We managed to do that without generating every possible assertion. So it's slightly more efficient than forward chaining. But now let's look at the hypothetical situation where, let's say that Trinity is disenchanted is not in our list of assertions. And there's no rule that could produce Trinity is disenchanted. Oh, I guess there is this one. Let's say we didn't have that. Okay, so hypothetical situation. We get to Trinity is disenchanted, and we're completely stuck. There's nothing we can do. What do we do now? Well, let's say we also had another assertion. Let's say we had an assertion A4 that Morpheus proclaims love for Neo. Plot twist. Now what happens?
Go back up to the question.
What's that?
6 could be an or node with 2 different assertions.
Yeah, so you could make this an OR node. That gets kind of complicated because it's not just a straight OR node because it affects what goes on in this part of the tree. So probably a better way of representing it would be to just make another copy of the tree. Instead, we're just going to make this tree kind of messy and cross stuff off. We're going to backtrack. So we're going to put an asterisk on this depth first recursion. So in general, we're just doing a depth first search, except when we get stuck. Then we'll backtrack and try to find different bindings. So if we get stuck, backtrack and bindings. So in this case, that means that we're going to go all the way back to here where we tried binding the variable y. And we're going to try a different binding. So we can try instead y equals Morpheus and see what happens. So what would be, in that case, the 11th hypothesis that we're checking? Is that y or Morpheus? So that's going to be y proclaims love, because once again, we don't care who's proclaiming love. We just want to see if there's someone other than Trinity who might be able to make this work. So here we're going to end up with y proclaims love back in our list. So then that means that this y has to be Morpheus. So then we'll check. This is number 12. So what's the 12th hypothesis? Is that y or Morpheus?
Morpheus.
That one's Morpheus because they have to be the same. So then we have Morpheus picks the one, and you could go on and see what happens with that. Any questions on that? Okay, so a couple other neat things. So I mentioned earlier not and delete rules, and we talked a little bit about those. I think I have an interesting example of not rule that we can look at. So let's say we have this rule. If X has chocolate, and if X happens to be a person who doesn't not like chocolate, we're going to write that as not X doesn't like chocolate. Then X is happy. Let's say we have the assertion A0, John has chocolate. And A1, John despises chocolate. Is this system going to conclude that John is happy?
Yeah.
Yeah. So this is complicated because as people who speak English, we go, well, obviously if John despises chocolate, then he also doesn't like chocolate. But the system is going to go, well, X has chocolate that could match John, and we don't have the assertion that John doesn't like chocolate, so sure, John is happy. So another interesting thing.
What if at some
Yeah.
point, like, you discover that, in fact, he doesn't like chocolate? Like, if that becomes an assertion.
I see. Like if you have another rule that says if X despises chocolate, then X doesn't like chocolate.
If those fire in different order, you could get different things.
Yeah, that's true. So that's why in forward chaining we have a specified order for firing. So it's true that if you fire the rules in a different order, you might reach different conclusions. So you just have to define the precedence of the rules so that you get a consistent result. Yeah.
So the absence of an assertion, not the opposite of an assertion, is what they're talking about with the not?
Correct.
Okay.
Yeah, so not represents the absence of the assertion. So an interesting thing you can do, let's say that instead this rule was just, if not X doesn't like chocolate, then X is happy. So as English speakers we would go, well, that means that everyone who doesn't like chocolate is happy. The thing is, this system is going to run forever because it doesn't know that we want X to be a name and that we want X to be a character that we care about. So it's going to say, well, we could have X equals the variable ZZZ. ZZZ doesn't like chocolate is not in our list of assertions, so ZZZ is happy. and it's just going to produce every single string is happy and go on forever and do that. So we're going to say that this is a malformed rule and you can't have just a not. You'll also see that in lab 1, which is coming out tonight. So I think that's about it. I'm going to mention a couple things about 6034 in general.